Hello everybody, welcome to another episode of Extreme Math. Today I'm going to be talking about a really cool game called the Banach Mazur Game. And it's a type of topological game that's popular in the math community. And what's interesting about this game is that if certain conditions are met, you can guarantee that one person will win the game. Well, I'll go over what that means, but first I'll go over the rules of the game. Let's say that we are player A and we are given a subset of real numbers, and we'll call that A. And player B is given the complement of set A. And so, as player A, we will begin by choosing a closed interval. It can be any closed interval, and we will call that I1. And then player B will then choose a closed interval that's a subinterval of I1, and we will call that I2. And then we will again choose a closed interval that is a subinterval of I2, and we will call that I3. And we will keep doing this on and on. In general, the set that we choose will be indexed by an odd number, and we'll call that 2n plus 1. And so player B, which always choose the set in general, I sub 2n. So we will keep doing this to infinity as n goes to infinity. And at the very end, if at the very end, the final set contains an element of A, then we will win. And to express this mathematically, it means that if the intersection of A and then the infinite intersection from n equals 1 to infinity of I sub n is non-empty, then player A wins. So by now, have you spotted the winning strategy? It's pretty simple. Since it's an infinite game, as player A, all you have to do is wait for player B to get bored and then forfeit, and so you would win. So that's all I had for today. Thanks for watching. Please like and subscribe. Okay, so I'm kidding, but let me go over some examples before I go over the winning strategy. Here's an easy example. Let's say that in set A, there is an open interval J, and by the definition of an open interval, every point of J will be an interior point, which means that there will always be these tiny little subintervals can form this tiny subinterval for every point in J that you choose. And so what you would choose then as player A, you would just choose J, because then no matter what player B chooses, you can always find these tiny subintervals, right? And so they will contain points of A, and so you have a winning strategy. Let me go over a more complicated example. Let's suppose this time both players are given bigger sets. So we are given the set of irrational numbers, and player B is given the set of rational numbers. So how will we win this time? You can actually express the set of rational numbers as an infinite union of the individual rational numbers. So infinite union of Qn, where Qn will be an arbitrary rational number. And so, in order for player A to win, what we have to do is the very first interval that we choose, we will make sure to miss Q1. We will miss it. The interval that we choose will not contain Q1. And then player B chooses an interval. And then we choose another subinterval that misses Q2. And then player B goes, and then when we go, we would choose a subinterval that misses Q3. And then that's the pattern. Every time we go, we would make sure that we miss another point of player B. So we will miss another rational number. And so in general, if every time we miss rational number q sub n for the interval I sub 2n plus 1 that we choose. If that were to happen, and then n will go to infinity, then what this would mean is that the final intersection, the infinite intersection of in, will contain no rational numbers at all. And so this only shows that the intersection doesn't contain any rational numbers. But how do we know that it contains irrational numbers? Because that's the way that we win. We have to make sure that it contains an element of A. So how do we do that? Well, that's actually the trickiest part in the proof, because in order to know that, you would have to know the Cantor's intersection theorem. So if you don't know it, you can research it on Wikipedia or something. But basically, if you have a bunch of nested closed intervals and it goes to infinity, then at the very end it will be non-empty. So that's what this is. The infinite intersection of in will be non-empty because of Cantor's intersection theorem. And since it contains no rational numbers, it must contain an irrational number. And so we, as player A, have a winning strategy. Now, the reason why we have a winning strategy is because we're able to miss these elements of B. So we're able to miss these individual rational numbers. And that's because each of these QNs is nowhere dense. And if you remember the definition of nowhere dense, every interval will contain a subinterval that does not contain any elements of the nowhere dense set. And so every time we choose, we're able to choose an interval that misses Qn because of the fact that it is nowhere dense. And in general, here's a winning strategy. Player A is able to win if the set B is a countable union of nowhere dense sets. And we call that sort of set first category. So we can win if player B is given a first category set. So that's all I had about the Banach Mazur game. And this is a type of topological game. You can search that yourself to learn more and play this at the next party you go to. In the next video, I'm going to be going over how this game can actually be used as a proof for the bare category theorem, which is a really cool theorem that's prevalent in mathematics. So stay tuned for that, and I'll be posting that shortly. Thanks for watching.